SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering module number 3. This is the new module that we are going to start after taking the discussions on steam power system. So, in this module number 3, we will emphasize on another kind of technique or technology to generate power. So, that is gas turbines and combined power system. So, basically in this module we will try to emphasize that same combustion process. If you can do another technology or another method, what is the possibility that we can have? One possibility is that we can have based on gas turbines system is that it can serve for power generations as well as for thrust generations. In fact, gas turbines is the backbone of aircraft industries because they generate thrust through this gas turbine technology. So, our module will emphasize on two different themes. One is gas turbines for production of power, other is gas turbines for production of thrust. So, let us start this first lecture. So, in this lecture we will touch upon fundamentals of gas turbine systems, and here we will try to emphasize on gas turbine cycles, various gas turbine cycles that are possible with their possibilities. Then one important thing is that for gas turbines reference cycle, we take it as a Brayton cycles. For example, for steam power systems, the reference cycle was ideal Rankine cycle. So, similarly, and that was treated as steam power cycle, and for gas turbines the corresponding ideal cycle reference cycle is the Brayton cycles. Then subsequently we can analyze its thermodynamic aspects to know that what is the work output and power and efficient work output, power developed and subsequently efficiency of the cycles. Also we will touch upon the possible working fluids that can be used for gas turbine systems. So, just to give the brief introduction of gas turbine cycles. So, gas turbines provide wide range of services for mainly for industrial plants, for driving mechanical devices like pumps, compressors, electric generators, and they have also capability of producing electric power for peak load requirements. Normally, whenever the steam power fails, additional power can be supplied through gas turbines, and that enhances the peak load requirement. Also, other application of gas turbines that normally steam power plants do not have is the thrust generations. So, all aircraft engines are powered by this gas turbine technology, and they are mainly used for thrust generations. Now, apart from that, additional advantage of this gas turbine units is that they are used as a combined cycle plants. That means, in combination with steam turbines, regenerators, heat recovery boilers, there are various augmentation techniques that steam turbines can be combined with gas turbine technology for a combined cycle power generations. Many times we also call this as a co-generations. With this background, let us see that some of the advantage of gas turbine plants is that they are small in size, requires less mass, low initial cost per unit power. They are available for with short delivery times. That means, you do not once you start this engine, then within quick time it can start, and also it has a smooth running as compared to steam system. They have compatibility with wide range of liquids and gaseous fuels, synthetic fuels. They have flexibility for the supply of process needs. That means, in a gas turbine units, we normally compress the compressor is used for compressing the air, but if for process needs, wherever it is required that high pressure air requirement is there, then we can tap this compressed air for its use. And also these gas turbine plants have very less environmental restrictions, but however, there are, apart from this advantage, there are some disadvantages as well, because they have difficulties in primary base load prime movers. That means, although they can be used safely for augmentation plant or supplying the extra energy, but primary requirement you cannot have this gas turbine unit, because the starting torque is normally less. So, they are incompatible with solid fuels, but they are only suitable for peak load requirements. They have lower efficiency compared to steam power plants, but if you want to improve the efficiency, it requires some boosting. That means, initial gas temperature needs to be higher. So, that has to be achieved and that needs an extra cost. So, these are the some of the disadvantages, but however, gas turbine technology is a very useful technology, and it has been commonly used in many applications, and main applications that happens here is that most of the marine engines also are driven by the gas turbine plants, because for production power. Aircraft engines, they require the gas turbine technology for thrust generations. Side by side, steam power systems requires gas turbine units for its operation in combined mode, which can produce the peak load requirements. So, these are the some of the themes or advantages that gas turbine systems have. Now, let us try to understand the thermal circuits for a gas turbine cycles. The first category of first type of configurations that we can have, this gas turbine can have single shaft requirement or single shaft configurations, or it can have two shaft configuration. These are the two possibilities normally gas turbines operates. So, let us try to understand what these two things means. Normally, if you look at a gas turbine units, there is a four basic component. One is compressor, second is turbines, third is combustion chamber, and there is a shaft, fourth one is the shaft. So, what happens that air enters to the compressors at state 1, and normally it is atmospheric air. Now, after compressions it enters into the combustion chamber, that is at state 2, and this in this combustion chamber normally we add fuel. So, when we have the fuel, this is similar to IC engines, where fuel and air mixture, fuel plus compressed air gets combusted, and this from these things we get the exhaust, we get the combustion products at state 3. So, these combustion products expands in the turbines and exhaust comes at state 4. So, basically speaking that and the power is getting developed by these turbines. So, what happens is that here the turbine has two roles to play. One is it can give the load requirement for the plant. Second is this turbine also drives this compressor through the shaft. So, ideally speaking, the turbine speed and compressor speed should match, so that single shaft can be connected, and at the same rate we also the turbine also produces the power. So, power development that comes from the turbine, and compressor takes the work input. So, part of this turbine work goes to compressors to drive it, and rest of the things balance part, that is W t minus W c is your resultant power that is being produced. So, this is what the single shaft arrangement needs to have, and it is a why we call as a direct open cycle, because both the sides like inlet and exhaust, they are atmospheric in nature. There is no additional or secondary fluid comes into picture. But in two shaft arrangement, the process remains same as it is. Air enters at state 1, after compression it leaves at state 2, and in the combustion chamber fuel plus air gets added. So, fuel gets added to the high compressed air. So, it leaves at state 3. Now, here we have the changes. First is we have a low pressure, we have a high pressure turbines, and this high pressure turbine produces power just to drive the compressors. So, we have W t 1 and W t 2, that is 2 turbines, that is let us say W t 1 means I will say W h p and W L p, low pressure turbine. So, high pressure turbine drives the compressors. So, if I say total power from the turbine is W h p plus W L p, and this W h p high pressure turbine is equal to W c. That means, compressor power requirement is achieved through this high pressure turbine, and this further after expansion is not still complete. We take out this air, take out this combustion products and further expand in another turbines. So, essentially the outside load requirement is achieved through low pressure turbines. So, advantage for these things is that here in the single shaft arrangement, we cannot run the systems at varied load, but here in a two shaft arrangement, since the two shafts are decoupled to each other, that means only compressor and high pressure turbines can run at same RPM, but whereas the turbine connected for load requirement, that it can run at different RPM. So, this allows the loads to be driven at variable speeds. So, this is the single shaft and two shaft arrangements, and we call both of them as direct open gas turbine cycle. Now, this also have another point I need to emphasize here, that in this figure what we have shown here, these gas turbines are used for power generations, but there are possibilities that this instead of getting power through turbines, the exhaust gas can also expand further in a nozzle for thrust generations. That is essentially happens in an aircraft engines. So, the useful power can be supplied by the turbines or allowing the gas to expand further in a nozzle that can provide propulsion or thrust for these aircraft engines. This is the another advantage of the gas turbine systems. In fact, all aircraft engines rely on gas turbine units. So, gas turbine technology is the backbone for aircraft systems, and again we call this as open cycle, and because we need to rely on atmospheric air which continuously is taken, and since we are dependent on atmosphere, air is the only feasible choice. Now, this is about direct open gas turbine cycles. Another thermal circuit possibilities we can have indirect open gas turbine cycle. The word indirect is being used is that we here we do not have a combustion chamber, rather we have a heat exchanger. And what does this heat exchanger does is that normally these things are used when the gas turbine technology is used in the combined power plant board. So, what we have is that somewhere we are having another kind of working fluid and we call this as a coolant, and this is which is being produced from any other reacting systems. So, initially air which is taken from the atmosphere enters in the compressor as state 1, after compression it goes to state 2. Now, instead of air getting combusted, it takes heat from another medium or another working fluid, and normally we call this as a secondary fluid or coolant for this cycle, and there it only takes the heat. So, thereby it becomes a high pressure air and high pressure and high temperature air, and that enters into the turbine, then expands. So, the load requirement is again same W T, and here W C is the compressor work. So, difference between them is the work that is getting produced, W T minus W C, but here only the difference is that the air and the primary fluid and the secondary fluid, they do not mix each other, only heat is getting tapped. So, this is what the indirect open gas turbine cycles. So, the word open means atmospheric, we rely on atmospheric air. The word indirect means it is air is not used directly, rather heat is taken to the air from the another fluid. The next thermal circuit arrangement is direct closed gas turbine cycle. So, it is a direct closed gas turbine cycle means we have a reactor. Of course, this reactor can be interpreted as combustion chamber as well. So, in this case, so it is a direct closed gas turbine cycles. What happens is that where we have air plus fuel which are mixed in this reactor, and this compressor and turbine have single shaft, and the turbine drives the compressor as well as it produces the power. But extra change that we have here, we do not rely on atmospheric air. So, basically here we do not, here we have choices is that we can, instead of air, here we can a possible choice of gases, any other gases that can continuously be circulated in these cycles. So, let us say we say there is some gas enters in the compressor, after compression it goes to state 2, it enters to a reactor, where basically this reactor, here I use the word reactor instead of combustion chamber, is the heat addition that takes place. Then after heat additions, this high pressure and high temperature gas enters to the turbine at state 3, and after expansion the exhaust gas, the gas comes out from the turbine, but here instead of going out atmosphere, the same gas gets recirculated. So, the piping arrangements are different, for one for the working fluid circuit, other for the rest of the components in the circuit. So, this is what we call this as a direct closed gas turbine cycles. And next and most important arrangement that we are going to discuss in our cycle is the Brayton cycle. What it does, it is an indirect closed cycle, closed gas turbine cycle. So, what we take the techniques or thermal circuits from a direct closed gas turbine cycle and indirect open gas turbine cycles, combine them, then we get this indirect closed gas turbine cycles. So, what it does is that, and the indirect gas turbine cycle combines the indirect open cycle with direct closed cycle, so that the reactor is separated from the working fluid by a heat exchanger and the working gas rejects it to the atmosphere via heat exchangers. So, we have one working fluids which revolves in this circuit, another working fluid we have in this reactor circuits. So, basically two different working fluids and they do not mix each other, and this is what the most efficient gas turbine cycle we can have, and main advantage for this is that it is mainly used for power generations. Other advantage is that we are not supposed to rely on one particular gas, we can have multiple possibilities of gas to optimize the power and efficiency requirement. And this is what we call as a Brayton cycles. So, the indirect closed gas turbine cycle is the benchmark or analysis part for a Brayton cycles. So, the ideal cycle for a gas turbine power output is the Brayton cycle. It composed of, you can see here, we have state 1 where gas enters, after compression the gas comes out. So, this process is called as compression process, that is from 1 to 2. So, here pressure shoots up and it is an isentropic process. Then from 2 to 3 it enters to a heat exchanger where heat is getting added to the gas, that is we say Q in. So, Q in is the process 2 3. So, it is a heat addition process at constant pressure, and here we have compressor, that is takes W c. Then after heat addition process the gas enters to the turbine for expansions. So, heat addition process is constant pressure process. Now, in the turbine process is denoted by 3 4, and this process is isentropic process, that is constant entropy process, that is in the turbine, and again finally heat rejection process that takes place at constant pressure. So, effective work that we get is from expansion and in the turbine, and heat addition process that takes place is Q in, that is from in the heat exchanger. So, this is the very basic bottom line for an ideal Brayton cycle, and here the components are treated to run as a steady flow manner with negligible kinetic energy, change in the kinetic energy, and work done is so that the work done from the turbine is equal to change in the enthalpy. So, you now here we need to do some assumptions. When you say the gas that continuously enters in the compressor and turbines, that specific heat for the gas should be assumed to be constant for the range of operations that we are looking at. So, with constant specific heat assumptions, the analysis becomes a simple air standard cycle with air as working fluid. Further, we need to do this thermodynamic analysis. For this thermodynamic analysis, let us refer to this pressure, volume and temperature entropy diagrams. Process 1 to 2 is compressions, which is W c work enters. Process 2 to 3 is constant pressure heat addition. 3 to 4 is expansion in the turbine. 4 to 1 is heat rejection Q out. So, this is what we see in the pressure volume diagram. Similarly, 1 to 2 is isentropic process, in the compressor, 2 to 3 is the heat addition process in the combustion chamber, 3 to 4 is the expansion process in the turbine, and 4 to 1 is the heat rejection process at constant pressure. So, with this analysis we can recall some of the fundamental parameters. First thing, we have to say or define the pressure ratio for the turbine, that means what is the range of pressure it should work, that is we define a term which is called as pressure ratio for turbines. There are possibilities pressure ratio in the compressor and turbine, they may or may not be equal, but however, for our analysis we will say that since the compressor is driven by the turbine, so we say that the pressure ratios we need to remain same. And second, for isentropic expressions we can have the temperature ratios can be expressed in this pressure ratio. Then we can, by using this pressure volume and temperature entropy diagrams, we can calculate what is the work that is done in the turbine, m times Cp T3 minus T4, because the enthalpy, since it is a gas mode, and gas, when you say gas mode, we can write enthalpy as Cp times T. So, it is a enthalpy is a function of temperatures. So, we can arrive at work done from the turbines, and subsequently this can be interpreted in terms of pressure ratio. Now, one important expression that I need to emphasize here, work done in the turbines is m dot Cp times T3 into 1 minus 1 by Rp to the power k minus 1 by k. Here k stands as the specific heat ratio, that is Cp by Cv, and R is equal to characteristics gas constant, that is Cp minus Cv. But one thing I need to emphasize here, that power developed from the turbine depends on the maximum cycle temperatures. So, in this diagram if you see, T3 is the T max. So, higher you go to the maximum temperature, power requirement will be high. And second thing, it also depends on the pressure ratio. Now, if you can make this, if you can go for higher pressure ratio also, power we can develop is more. In the similar analogy, we can also find that what is the work that is to be given for the compressor. So, that also we can find out, that is m times Cp into T2. So, T2 is the temperature of the gas that comes out after the compressions. So, we have work done in the turbine, work done for the compressors, then we can find out the net work done for the cycles, W net is equal to Wt minus Wc, and we also can have heat added to the cycles, it is 2-3 process, that is Cp m dot Cp times T3 minus T2, and from noting down the net work and QA, that is heat added, we can define this thermal efficiency for the cycles. So, the thermal efficiency we can arrive at is that it is given by 1 minus 1 by Rp to the power k minus 1 by k. Now, further the net work is also written in, since here we have expressions are T3 and T2. So, it is and T2 is an intermediate number which normally we do not know. So, what we normally know is what is the minimum temperature and maximum temperatures. So, T3 is your T max and T1 is your T mean. So, an idealistic way of, or most effective way of representing network is in terms of T3 and T1, which is the highest and the lowest temperature of the cycle, and also pressure ratio is the another role that needs to be accounted. So, basically net work is a function of maximum temperature T3, minimum temperature T1 and pressure ratio. Additionally, it also depends on the working fluid. So, that is the function of Cp. So, the characteristics of working fluid comes into here with respect to K, that is specific heat ratio, and Cp. These two numbers is very vital for the choice of the gas which is being used in as a working fluid. So, with this we will try to emphasize what are the different inferences that we get out. So, basically whatever expressions we have done so far, and if we can just plot them graphically, we try this curve because we have parameters like pressure ratio, maximum temperature, minimum temperatures, then we have working fluid. So, based on this we can find the curve for efficiency and specific work. So, if you keep on doing it, the curves normally looks like this. So, what inference that we get out of it is that first is on thermal efficiency of the working of the cycle for a given working fluid, that is constant Cp and specific heat ratio, it increases asymptotically. So, basically if from this curve, the with common x axis, that is pressure ratio, efficiency is plotted here. So, this is plotted for air as well as helium. It is plotted, and this dotted line refers for efficiency curve and solid line refers for the specific work. So, if you look at dotted line, and that is for efficiency curve, we can see that helium is always happens to have more efficient than air as working fluid, and this curve continuously increases, and in fact it does not depend on the cycle temperatures. You can see here in these expressions, just keep on increasing for a given value of K, just keep on increasing Rp, we will have this efficiency curve. Then second inference, if we will look into it, is the specific work. Now, when you look at the specific work using these expressions, we find is that specific work initially it keeps on increasing, and one particular point it starts dropping. That means, if you keep on increasing the pressure ratio, after some point of the pressure ratio, the work output comes down. And here, and this is true as for helium as well as air. Now, compared to the helium and air, you see that helium will have high value of Cp and K. So, because of these reasons, and in fact it is since Cp value is almost 5 times more, if you can see peak power for helium is almost more than 5 times. So, this is the advantage, but however, the way it rises it also falls suddenly. So, that means we have the possibility, that means if you have a choice of air and helium, it is better to choose the helium as working fluid, because at a given pressure ratio the helium will have a higher capability of producing work. That we can see here. That means, if you see this particular plot, temperature entropy diagram shows effect of pressure ratio in the Brayton cycles. So, basically T3 is the maximum temperature, that means the turbine supporting systems or metallurgical requirement blades that we need to be operated. So, that is fixed by maximum temperatures. Now, when we have minimum temperature, that is fixed by the atmospheric conditions. So, within this maximum temperature and minimum pressures, there can be any number of Brayton cycles. One which is one with much wider, other is with like abscissa and ordinates value may be different, but the curve for the work output shows that we have either whatever working fluid we have, air or helium, there is an initial rise and then followed by a peak work, then it has to come down. So, this is the choice. This particular TS diagram shows here is that there are 3 cycles, cycle 1, cycle 2 and cycle 3, and cycle 1 has a wider range and cycle 2 will have smaller range. So, but what we can have, we will get the optimum work in the cycle 2 only. So basically this is true because we want to operate the cycle only for a maximum power for which the pressure ratio is optimum. So that is the reasons we normally operate the gas turbine cycles for maximum power, and that maximum power can be obtained by differentiating with respect to pressure ratio, and it turns out to be a conditions like T 2 is equal to T 1 into T to the T 3 to the power half. So based on this we arrive at the expressions for optimum power ratio RP optimum, which is a function of maximum temperature and minimum temperature to the power k by twice into k minus 1. So very basic summary is that use of working fluid in a gas turbine unit or the choice of working fluid in the gas turbine unit is to design the cycle or design this Brayton cycle in such a way it should produce maximum power, and for that maximum power we have to use this optimum conditions of pressure ratio. So that is the advantage that in fact for other pressure ratios the power can be the cycle can be operated, but the better approach is to choose a working fluid which has more capability in terms of specific heat and specific heat ratio. So these things I have already explained is that at same value of temperature limits, pressure ratio and specific heat ratio, the net specific work is directly function of specific heat. Net specific work is a direct function of specific heat, which means helium can produce 5 times higher power than that of air. Similarly, for same values of temperature limits, pressure ratio, specific heat, working fluid with higher values of specific heat ratio have advantage of producing more specific work. So there we have this ratio, that is Rp pi to the power k minus 1 by k. So this ratio plays a very vital term because specific heat ratio for helium is higher. Another point that need to emphasize in terms of working fluid, we have already only told about air and helium. Then what are the other possibilities? Other possibilities can have, so air and helium, normally we say helium is a monoatomic gas, air is a diatomic gas, air or nitrogen can be diatomic gas. So we can also have triatomic gas. So there are possibilities that we can have multiple different types of gas that can work in the Brayton cycle. But what happens is that when we use monoatomic gas like helium in this case, obviously for a given pressure ratio, let us say I take this pressure ratio as 4, at this pressure ratio with air as working fluid, it can produce closely about 350 kilojoule per kg of work, but at same pressure helium has the capability to produce closely to 1800 kilojoule of per kg work, which means, but if you want to produce with same for air, we have to go for higher pressure ratio. So which means that plant size or reduction of for reduction of the plant size, we need to rely on monoatomic gas for a given pressure ratio, because monoatomic gas has advantage of higher specific heat and also will have higher values of K. So this is the background summary for the thermodynamic analysis. So now we will rely on a numerical problems which is based on the working principle of an ideal Brayton cycle. The question that was given here, we need to find out the pressure ratio required for an ideal Brayton cycle to produce net work of 1400 kilojoule per kg. And we are given with data that cycle has maximum and minimum temperature of 288 and Kelvin and 1380 Kelvin. We also need to find out optimum pressure ratio and maximum work. So, we have given the choice of working fluid with helium and air. To solve the problem, so first thing we need to do is to draw this pressure, volume and temperature entropy diagram. So, that is 1 to 2 compression, 1 to 2 is the compression, 2 to 3 is the combustion, 3 to 4 is the expansion, and in the turbine 4 to 1 is the heat rejection. And in these temperature entropy diagrams, the cycle can be drawn in this manner like 1, 2, 3, 4. So, here we say S is equal to constant, that is entropy is constant, here pressure is equal to constant. So, basically we have Q in and we have W c that enters into the system, W dot c, W dot T that is power that is being produced. So, with these notations, the data that is given is that T 1 is 288 Kelvin, T 3 is equal to 1380 Kelvin, and we are supposed to produce this much power W net, that is 1400 kilojoule per kg. And working fluid, that is we have air and we have helium. So, first thing let us start that working fluid. If you take helium, if you take working fluid helium and try to find out the optimum pressure and maximum work, then we note down this value. Specific heat ratio for helium is 1.66 specific heat ratio, and Cp value is 5.2 kilojoule per kg Kelvin. And we also know that the expression for Rp optimum, that is equal to T 3 by T 1 to the power k by k in twice into k minus 1. So, with this data T 3 and T 1, then we can find out Rp optimum value for helium is 6.6 by inserting T 3 T 1 k. So, and for these things we have to now write down what is this W dot n by m dot, that is maximum power, that is Cp times T 1 1 minus Rp to the power k minus 1 by k plus T 3 into 1 minus 1 by Rp to the power k minus 1 by k. So, you have all the numbers here, Cp 5.2, T 1 288 RP optimum, that is 6.6, T3 1380. So, this will give you W dot N by W M dot maximum. So, this value is 3242.5 kilojoule per kg. So, this answer gives you the fact that with we can use helium as working fluid. With this optimum pressure ratio, it can give maximum power is 3424.5 kilojoule per kg. So, these two answer we got it, but our requirement is that we need to produce 1400 kilojoule per kg. Then why then what pressure ratio we should have? So, again for that reason, for that answer, if I put W dot N by M dot as 1400 and putting and calculating, find RP. So, to do that we can write this expression, that is 5.2, that is Cp, T1 is 288 into 1 minus 1 by Rp. Note that here Rp is unknown. Rp to the power k minus 1 by k plus T3, here k minus 1 is 1.66 minus 1 by 1.66, T3 1380 into 1 minus 1 by Rp to the power 1.66 minus 1 by 1.66, and if you take that as 1400, then find Rp by iterative process. So, to start this iterative process, we use different values of Rp, but initial choice for this Rp is that we all know that for Rp of 6.6, your W net is 3242.5. So, but our requirement for W dot N by M dot, W net is 1400. So, if you keep some values which is lesser than 6.6 and keep try finding whether left hand side expression matches with the right hand side, that is 1400, then that will be your answer. So, this will give you by iterative process, if you keep on iterating, and Rp will be approximately 2.2. So, the pressure ratio required for helium is 2.2. Now, same thing if I try for air. For air, we say Cp is 1.005 kilojoule per kg Kelvin, K is equal to 1.4. We can arrive at Rp optimum is equal to T3 by T1 to the power k into twice k minus 1, 1380 divided by 288 to the power 1.75. So, this number is 4.77. Now, at this optimum pressure ratio, W dot N by M dot we can find out that is equal to 1.005 into 288 1 minus R p to the power k minus 1 by k plus 1380 into 1 minus 1 by R p to the power k minus 1 by k. Take this R p is equal to R p optimum 4.77 and we arrive at W dot n by m dot is equal to 335.8 kilojoule per kg. So, here we need to have important inference here with helium as working fluid, and when you operate this cycle with a optimum pressure ratio of 4.77, we can have maximum power of 335.8 kilojoule per kg. That means, air cannot produce 1400 kilojoule per kg. So, for this problem the option of air is ruled out. So, we must use helium as working fluid at a pressure ratio of 2.2. So, these particular things we can also verify graphically. If you look at in this graph, for pressure ratio of 4.77, somewhere here close to 5, the possible value of specific work we can drop down, which is close to 335, and there is no possibilities that with air we can have specific work beyond this value, that is 500. But with helium, with this ratio of 2.2, we can easily go up to 1400. So, this is cross verified from these graphs. So, this is all about for the lecture today. Thank you for your attention.